Yeah, as already introduced, thanks. My name is Thomas Roehr. I'm from Robotics Innovation Center up in Bremen. And yeah, if you don't know what we do, on the right-hand side here on the slides, you already see a couple of the robots that we have. And by the way, also running what I will introduce shortly, which is named ROC here. Okay, most of you will be familiar, obviously, with developing with ROS. So I kind of outlined the ideal of ROS workflow. So you start by having a kind of functional decomposition of a problem, maybe already your ROS nodes in mind. So you start developing your algorithms, and then you want to put these algorithms into your ROS nodes and solve the problem using the ROS infrastructure. So possibly, well, you also want to use the ROS parameter server, and well, once you're done with designing your network, you eventually launch it using the ROS launch scripts. And yeah, now you have your networks, you have your ROS infrastructure up and running, and then you can use the existing tools like RosVTF, RxGraph, or the more recent versions in order to monitor what's going on online. So once you have worked with a couple of systems and gained some experience there, some questions might arise, at least for some of you guys. And so the question for some of you might, okay, I have now this rather big node network, and it got quite complex. So how do I actually effectively and efficiently start to manage this? So what do I mean by that? So can I actually validate what's going on in my network? Can I do that also before I actually start it, before it's up and running? And actually, since not for all tasks I need all of the nodes, do I actually have to have them all running at the same time? And eventually also, can I handle errors in my node network, not just network errors? Okay, there's a difference. So if you have these kind of questions, then this talk might be for you. So, and then an answer might also lie in the integration of ROS into ROC. And ROC is here, the robot construction kit. So I guess not many of you have heard of the robot construction kit. So well, I try to emphasize here is we have a ROC independent part, and meaning framework independent part, and some framework dependent part as well. I will focus now on the creation of components. Components meaning similar, well, to ROS nodes. And so stressing the fact that where we started is actually development at a framework independent level. So we develop libraries which are framework independent, and that is not, well, that is not ROC specific. That should be like commonly done in order to facilitate application of the functionality that is then developed. So in our case, language of choice is actually C++. We also have on the tooling side quite a lot of Ruby. So what is ROS for? What is Python and ROS mainly is also here Ruby. But from experience in general, you can't predict where frameworks will be going. So, or if one framework will come up and dominate the place. For example, Player Stage was it in recent, or years before. Now we have ROS, and so actually what we want is to enable our robots with what we have at the best that we can. And sometimes also industry doesn't agree with our choice of framework, so, well, we still can use our libraries. So we start there with the general component development. We put our functionality in libraries, but then we actually continue with a model-based workflow, meaning that we first specify what are the actual interfaces of our components, and using that kind of specification to generate a, well, code skeleton. And this skeleton is actually based on Oracle's RTT, so we have least one of the members, developers here in the audience as well, if you have specific questions there. And we integrate the functionality into the ROS RTT component skeleton that we generated there. So simplified illustration of the interface. You have properties to configure your component. You have input and output ports. That is a quite significant difference here, since we have a connection aware system. That means we have a dedicated connection management between our components. So there's no publish subscribe, but there is a, like we control where goes what, pretty much. So what you see here is one component that is now the infrastructure, or providing the infrastructure for a library that's called the message driver. This is actually ripped off the tutorials from our website as well. So the specification looks like this. You have a task context, which is actually, well, this is your component description in a way. You have your output ports, you have your input ports, you can specify them. You have states that you can specify on top of the already existing ones, which are there with ROS. And then you also can define properties. So that's the first thing that you do when you start developing this component, and from that you generate automatically the C++ skeleton. So once you have built your component and using this kind of infrastructure, what you get for free is actually, first of all, a quite streamlined and guided workflow up to that point, since you just fill out this kind of skeleton, and having that, you actually get a really consistent user experience. So what you learn once, you can continue learning, continue use in the further usage as well. So with this component model that ROS provides, and that doesn't mean that we enforce some kind of communication middleware, since ROS actually allows to plug in different communication middlewares. So default is Corba, but you can also switch to MQ for local systems. And so in the end, what we have here, or try to achieve here, is a scalable approach for system integration. What that exactly means, I come to in a minute. So out of the box as well, what you get is here node-led functionality, action-led functionality, and dynamic configuration functionality. So without adding anything, you have this kind of functionality there. If you want to get your fingers a bit more dirty, you can also have some kind of, well, you have transformer functionality and also a thing called stream alignment, which is, at least at the moment, still quite unique here. So regarding system integration, meaning now we want to build complex systems. Complex systems that allow us to control our robots. And what you can start with is actually small Ruby scripts. So that is an interface which allows you to set up small testing, test setups. And this Ruby interface gives you access to the processes and, well, components, and also gives you access to now, and here's the integration part, to ROS nodes. So at the same level that we are using ROS components, we are integrating the ROS nodes. So Ruby script looks like this. So for those not familiar with Ruby, well, actually it's also a domain-specific language that we define here using Ruby. But so require ROS is just loading our functionality in, then ROS initialize. Initialize is also the communication layer underneath, including Corba. We run so-called deployments. Deployments, well, actually the build components. In this case, we have the task context, which is called message consumer task, which is identified then as message consumer on the network. Same with the message producer task, which will be identified as message producer on the network. So using the inbuilt name service, you can then access these tasks and then perform operations on them, like configure in order to apply the configuration, start them, and, well, you can also do a so-called, well, clean up and stop on these components. So you have a dedicated interface for these kind of components to manage then your component network. So the ROS integration, just to show what it might look like, is here from our so-called task inspector, which allows to show all running nodes on a system. So there is the ROS master that has to be started, plus in this case we have a ProSilica, like the typical ProSilica drivers tutorial. If you follow that, you get a running ProSilica driver, and your camera provides an image. And what you need to do, though, is to implement the type conversion between the image format or image data type that ROS provides and the one that ROC uses actually internally. So what you see here, for example, in the just under output ports, the type name would be base samples frame in this case. So this is basically just looking at single components, but handling the real complex problems is, usually tackling robots, and then usually the problems get more complex as we think in the first place. So what we try to do is starting out simple and trying to reuse what we have already. So that means we can try to design parts of the overall network and try to reuse it. And also try to employ error monitoring and error recovery in that case. So I will just show you a video which tries to illustrate a bit of the functionality that that we have through a tool that is called the supervision, Ruby. So there is a Ruby, the language, and Ruby, the supervision plan management tool, which this is the core of. And so what you start out is you design subsystems separately. That means, in this case, for example, you try to put on, this is a bit too fast, we stop it. You put your individual subsystems together using your tasks, your components that you have designed beforehand. So you do this for each of the subsystems, and you kind of first can put them on the side once you have them tested properly, and then you start combining them actually into more complex networks. And in the first place, you don't even need to bother whether they share any components and stuff like that. You just model them individually. So what eventually will happen if you try to deploy all these networks together is that the supervision automatically identifies, okay, which components are actually shared, and so eliminates like that two components would need to be started. So it just merges the network of components there and gives a compact view kind of. So that also means, of course, if they share components, there might arise conflicts at runtime if there are errors in one of the dedicated components. But these errors can also be handled, meaning that each of these, okay, this is just starting again. Meaning that we can take action because the supervision is based on an event-based system, and we handle individual events in that case, and we do an error recovery based on the information we get there. So you have now the power to actually do multiple things. First of all, you can do offline system design. Since we use this model-based approach, what you generate in the first place is a validation of your network. That's what we call the network instantiation, which you can do before you actually deploy the network at runtime. Then you can also use it to distribute your system. So if you run one say, controller of this supervision at one system, and you have other attached systems, this can be transparently managed through this supervision layer. So you can have your components distributed. And for the networks, what it allows is you don't need to have all your components running at the same time. So if you have certain functionality that you need at a specific point in time, you say, I require now this kind of network that provides the functionality. Then this supervision takes care of actually performing the switch, like checks whether certain components would need to be restarted, would to be reconfigured, and eventually this allows a really, for the user, easy management of complex tasks. And on top of that, I mean, we have offline system design, but we also have extensive logging and displaying facility at runtime. And since there is a lot of happening in the system, like especially if you look at individual events which come low level, from low-level devices up to higher-level components, it will be hard to manage if you don't have these kind of logging facilities. So it allows you to have a really proper monitoring as well. Monitoring as in user view at the moment. So summarizing, we don't want to reinvent the wheel here. We try to use as much as we can what's out there. So that's why we also sit on top of ROS RTT as a component model, which has been already proven in industry and is also actually used in a different way though in ROS here. So what I try to show here is actually a scalable approach to system integration. And so you can start out quite simply with the Ruby-based interfacing or Ruby scripts, or you can then start go on with the complex system modeling capabilities. So we actually provide this this functionality, or we use this functionality in our institute on different robots, the one that you have seen already on the title page. And if you're interested, just check it out on our website. And if you have questions or concerns or some remarks, just send an email. I mean, this is yeah, well, we have our developers mailing list. You can just hook in there and just yeah, contact us. So really would be good if we can have some interaction there. Okay, now open for questions. I think that